The Milky Way is the vast island of stars that contains everything we know and everything we are. Every star you see in the night sky, every planet that has ever been discovered, and every trace of human history exists within this single structure. Yet for most of human existence, we did not even realize that it was a galaxy. To early observers, the Milky Way appeared as a faint band of light stretching across the sky, a glowing river of stars that seemed mysterious and distant. Only in recent centuries did we begin to understand that this band is not just a feature of the night sky, but the combined light of hundreds of billions of stars that form a vast rotating system. To understand the Milky Way is to understand our place in the universe. We are not located at its center, nor do we occupy any special position. Instead, our solar system is situated in a relatively quiet region of one of its spiral arms, far from the chaotic center and far from the outer edges. This location has played a crucial role in the development of life on Earth, providing a stable environment shielded from the most extreme conditions in the galaxy. Yet, even from this relatively calm position, we are still part of something unimaginably large and dynamic. When we look up at the night sky and see the Milky Way stretching overhead, we are seeing the galaxy from the inside. Unlike external galaxies that appear as distant spirals or glowing clouds, we are embedded within our own, looking through layers of stars, gas, and dust. This internal perspective makes it difficult to grasp the true shape of the Milky Way, but through careful observation and modern astronomy, we have been able to reconstruct its structure with remarkable detail. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure from which spiral arms extend outward. These spiral arms are not solid structures, but regions of higher density, where stars and gas are more concentrated. As the galaxy rotates, these arms maintain their shape through patterns of density waves, much like traffic jams that move through a highway even as individual cars pass through them. Within these arms, new stars are born, and older stars continue their long journeys around the galactic center. The scale of the Milky Way is difficult to comprehend. It spans approximately 100,000 to 120,000 light-years in diameter, meaning that light itself takes over 100,000 years to travel from one side of the galaxy to the other. Within this vast space, there are estimated to be between 100 and 400 billion stars, each with its own system of planets, moons, and potentially other structures. Our Sun is just one of these billions of stars, located about 26,000 light-years from the galactic center. This position places us in a region known as the Orion Arm, or Orion Spur, a minor spiral arm located between the larger Perseus and Sagittarius arms. The Orion Arm is not a major structural feature of the galaxy, but rather a smaller branch where our solar system resides. From here, the night sky appears rich with stars, yet most of the galaxy's mass and activity lie far beyond what is visible to the naked eye. The Milky Way is not static. It is in constant motion, rotating around its center at hundreds of kilometers per second. However, This rotation is not like that of a solid object. Different parts of the galaxy rotate at different speeds, a phenomenon known as differential rotation. Stars closer to the center complete their orbits more quickly than those farther out. Our solar system, for example, takes roughly 225 to 250 million years to complete one orbit around the galactic center. This period is sometimes referred to as a galactic year. Since its formation, the Sun has completed only about 20 to 25 such orbits. During each orbit, the solar system travels through different regions of the galaxy, sometimes passing through areas with more star formation or higher densities of interstellar material. These movements occur on timescales far beyond human history, meaning that the structure of the night sky slowly changes over millions of years, even though it appears constant to us. The Milky Way is composed of several distinct components. At its center lies the galactic bulge, a dense, roughly spherical region filled with older stars and complex structures. Surrounding the bulge is the galactic disk, where most of the galaxy's stars, gas, and dust are located. This disk contains the spiral arms and is the primary site of star formation. Beyond the disk lies the galactic halo, a vast, diffuse region containing old stars, globular clusters, and a large amount of dark matter that extends far beyond the visible boundaries of the galaxy. Each of these components plays a different role in the life of the Milky Way. The bulge represents the older, more evolved core of the galaxy, shaped by early formation processes and gravitational interactions. The disk is the active region, where stars are born, evolve, and eventually die. The halo acts as a kind of extended envelope, influencing the galaxy's gravitational structure and providing clues about its formation history. Understanding the Milky Way also requires understanding its history. The galaxy did not form all at once. Instead, it grew over billions of years through the gradual accumulation of gas, dust, and smaller galaxies. In its early stages, the Milky Way was likely much smaller and more chaotic, gradually assembling through mergers and accretion. Some of the stars in the halo are remnants of smaller galaxies that were absorbed into the Milky Way long ago, leaving behind streams of stars that still trace their original paths. These stellar streams are important evidence of the galaxy's dynamic history. They reveal that the Milky Way is not a closed system, but one that has interacted with and absorbed other galaxies over time. Even today, it continues to interact with nearby dwarf galaxies, slowly pulling them apart through gravitational forces. This process of galactic cannibalism has helped shape the structure of the Milky Way and will continue to do so in the future. Despite its enormous size, most of the Milky Way is empty space. The distances between stars are so vast that even at the speed of light, travel between them would take years or even millennia. This emptiness is not truly empty, however. It is filled with thin gas, dust, magnetic fields, and cosmic rays, all of which contribute to the complex environment of the galaxy. These interstellar materials play a crucial role in the formation of new stars and planets. From our perspective on Earth, the Milky Way appears as a faint glowing band because we are looking along the plane of the galactic disk. When we look toward the center, we are looking through a much higher concentration of stars, which creates a brighter appearance. When we look away from the plane, toward the galactic poles, we see fewer stars and a darker sky. This variation helps us understand the three-dimensional structure of the galaxy. Modern astronomy has allowed us to map the Milky Way in unprecedented detail. Using telescopes that detect different wavelengths of light, from visible to infrared and radio, scientists have been able to peer through dust clouds that once obscured our view. These observations have revealed the spiral structure, the distribution of star-forming regions, and the presence of large-scale features that were previously unknown. Yet despite these advances, there is still much we do not know about our galaxy. Some regions are difficult to observe directly due to dust and distance. Others are hidden behind the dense central bulge. Even the exact number of stars in the Milky Way remains uncertain. Each new discovery adds to our understanding, but also reveals new complexities. The Milky Way is not just a collection of stars. It is a living system, constantly evolving over time. Stars are born in dense clouds of gas, live out their lives over millions or billions of years, and eventually die, returning material to the interstellar medium. This cycle of birth and death drives the chemical evolution of the galaxy, enriching it with heavier elements that are essential for planets and life. In this sense, the Milky Way is also the origin of everything we know. The elements that make up our bodies, our planet, and everything around us were formed in the cores of ancient stars and distributed across the galaxy through supernova explosions. We are, quite literally, made of the material that has been processed through countless generations of stellar evolution within the Milky Way. As we begin our journey into understanding this galaxy, we are not just studying an external object, we are studying our home in the cosmos. Every discovery about the Milky Way is also a discovery about our own origins, our place in the universe, and the long history that led to our existence. The galaxy is not separate from us. It is the environment in which we exist, evolve, and explore. And yet, even as we uncover more about its structure and behavior, the Milky Way remains full of mystery. Its true shape, its total mass, and its future evolution are still areas of active research. We stand inside this vast system, trying to understand it from within, piecing together its story one observation at a time. It is a story that stretches across billions of years, and we are only beginning to read its first chapters. To understand the Milky Way in full, we must look beyond its appearance in the night sky and examine its internal structure in detail. What seems like a faint band of light from Earth is actually a complex layered system of stars, gas, dust, and dark matter organized into distinct regions that work together through gravity and motion. The galaxy is not a uniform sphere or a simple disk. It is a dynamic structure with multiple components, each playing a different role in its formation, evolution, and ongoing activity. At the most basic level, the Milky Way can be divided into four main parts: the central bulge, the galactic disk, the spiral arms, and the halo. These components are not separate objects, but interconnected regions that blend into one another, forming a continuous system held together by gravity. Each part contains different types of stars and materials, and each reflects a different stage in the history of the galaxy. The central bulge is located at the heart of the Milky Way. It is a dense, roughly spherical region filled mostly with older stars. These stars are often red and yellow, indicating that they are in the later stages of their life cycles. The bulge is crowded and energetic, with stars packed much closer together than in the outer regions of the galaxy. At its very center lies a supermassive black hole, which plays a crucial role in shaping the dynamics of this region. The bulge is not smooth or uniform. It has a complex structure, including a bar-shaped formation that extends through its center, influencing the motion of stars and gas around it. Surrounding the bulge is the galactic disk, a wide, flat region that contains most of the Milky Way's visible matter. This disk is where the majority of stars, gas, clouds, and dust reside. It is also the primary site of star formation. Within the disk, material is constantly moving and interacting, creating regions where new stars are born and older stars continue their long evolutionary paths. The disk is relatively thin compared to its width, giving the galaxy its characteristic flat appearance when viewed from the side. The disk is not uniform. It contains spiral arms, which are curved regions of higher density that extend outward from the central bar. These spiral arms are not fixed structures like the spokes of a wheel. Instead, they are dynamic patterns created by density waves that move through the disk. As gas and stars pass through these waves, they are temporarily compressed, triggering bursts of star formation. This is why spiral arms appear brighter and more active than the regions between them. There are several major spiral arms in the Milky Way, including the Perseus Arm, the Sagittarius Arm, and the Centaurus Arm. Our solar system is located in a smaller structure known as the Orion Arm or Orion Spur, which lies between two larger arms. These spiral arms are not perfectly symmetrical or evenly spaced. They vary in shape and size, reflecting the complex gravitational interactions that shape the galaxy over time. Beyond the disk lies the galactic halo, a vast, diffuse region that extends far beyond the visible boundaries of the galaxy. The halo contains older stars, globular clusters, and a significant amount of dark matter. Unlike the disk, the halo is not flat. It is roughly spherical and much more spread out. Stars in the halo move in more random orbits compared to those in the disk, often following elongated paths that take them far above and below the galactic plane. Globular clusters are one of the most striking features of the halo. These are tightly bound groups of hundreds of thousands or even millions of old stars. They orbit the galaxy as independent systems and are among the oldest known objects in the Milky Way. Their ages provide important clues about the early history of the galaxy, suggesting that they formed during the earliest stages of its development. The halo also contains large amounts of dark matter, an invisible substance that does not emit or absorb light but exerts gravitational influence. Although we cannot see dark matter directly, its presence is inferred from the motion of stars and gas in the galaxy. Without dark matter, the Milky Way would not have enough mass to hold itself together at the observed rotation speeds. The halo of dark matter extends far beyond the visible parts of the galaxy, forming a massive gravitational framework that shapes its structure. The interaction between these components creates a galaxy that is both stable and dynamic. The bulge provides a dense central region, the disk supports ongoing star formation, the spiral arms organize material into patterns of activity, and the halo extends the galaxy's influence far into space. Together, these regions form a system that has evolved over billions of years and continues to change today. One of the most important processes shaping the structure of the Milky Way is rotation. The galaxy spins around its center, but not like a solid object. Instead, different parts of the galaxy rotate at different speeds. This differential rotation causes the spiral arms to form and persist over time. Stars closer to the center orbit more quickly, while those farther out move more slowly. This difference in Getty helps maintain the spiral structure as material continuously flows through regions of higher density. The rotation of the Milky Way is not perfectly smooth. It is influenced by the distribution of mass within the galaxy, including both visible matter and dark matter. Observations of stellar motion reveal that the outer regions of the galaxy rotate faster than expected based on visible matter alone. This discrepancy is one of the key pieces of evidence for the existence of dark matter, which provides the additional gravitational force needed to explain these rotation patterns. The structure of the Milky Way is also shaped by its history of formation and interaction. Over billions of years, the galaxy has grown by merging with smaller galaxies and absorbing their stars. These mergers leave behind streams of stars that continue to orbit the galaxy in distinct patterns. Some of these streams can still be observed today, providing evidence of past interactions that help build the galaxy into its current form. In addition to mergers, the Milky Way continues to interact with nearby galaxies, particularly those in the local group. These interactions can distort the shape of the disk, trigger bursts of star formation, and alter the orbits of stars. Although these events occur over very long timescales, they play an important role in the ongoing evolution of the galaxy. The interstellar medium, the space between stars, is another crucial component of the galactic structure. It is composed of gas and dust, primarily hydrogen and helium, along with trace amounts of heavier elements. This material is not evenly distributed, but forms clouds of varying density and temperature. In dense regions, gravity can cause these clouds to collapse, leading to the formation of new stars. In this way, the interstellar medium serves as the raw material for future generations of stars. The balance between star formation and stellar death helps regulate the structure of the galaxy. When massive stars reach the end of their lives, they explode as supernovae, releasing energy and heavy elements back into the interstellar medium. These elements are then incorporated into new stars and planets, gradually enriching the galaxy over time. This cycle of recycling material is essential for the chemical evolution of the Milky Way. Magnetic fields also play a role in shaping the structure of the galaxy. Although they are relatively weak compared to gravity, they influence the motion of charged particles and help guide the flow of gas within the interstellar medium. These fields are complex and interconnected, forming large-scale patterns that span the disk of the galaxy. From our perspective within the Milky Way, understanding this structure is a challenge. We cannot step outside the galaxy to observe it from the outside. Instead, we must rely on measurements of distance, motion, and light to reconstruct its shape. By studying the positions and velocities of stars, astronomers can build three-dimensional maps of the galaxy, revealing its spiral structure and overall organization. Modern surveys using space telescopes and radio observations have greatly improved our understanding of the Milky Way's structure. These observations have confirmed the presence of spiral arms, mapped the distribution of stars in the bulge and disk, and traced the extent of the halo. Yet, even with these advances, many details remain uncertain, including the exact number of spiral arms and the full extent of the dark matter halo. The structure of the Milky Way is not fixed. It is constantly evolving as stars move, gas flows, and gravitational forces reshape its components. Over millions and billions of years, the galaxy will continue to change, forming new stars, absorbing smaller systems, and gradually altering its shape. This dynamic nature means that the Milky Way we see today is just one moment in a long and ongoing process. In the end, the structure of the Milky Way reveals a system of extraordinary complexity and balance. It is a galaxy shaped by gravity, motion, and time, where every component plays a role in maintaining the whole. From the dense central bulge to the faint outer halo, each region contributes to the story of the galaxy's formation and evolution. As we continue to study this structure, we gain not only a better understanding of the Milky Way, but also a deeper insight into the processes that shape galaxies throughout the universe. Our home galaxy becomes a model for understanding cosmic evolution on the largest scales, connecting our local environment to the broader structure of the cosmos. At the very heart of the Milky Way lies one of the most extreme environments in the known universe. It is a region where gravity dominates all other forces, where space and time behave in ways that challenge intuition, and where matter is pushed to conditions so intense that normal physics begins to break down. This is the galactic center, a place hidden from direct view by dense clouds of gas and dust, yet revealed through radio waves, infrared light, and decades of careful observation. At its core sits a supermassive black hole known as Sagittarius A, an object that anchors the entire galaxy with its immense gravitational influence. The center of the Milky Way is located about 26,000 light-years from Earth. From our position in the Orion Arm, it appears hidden behind thick interstellar material that blocks visible light. For centuries, this region was completely unknown to astronomers. It was only with the development of infrared and radio astronomy that scientists were able to peer through the dust and uncover the dynamic and energetic processes occurring at the galaxy's core. What they found was not a simple, quiet center, but a densely packed and highly active region filled with stars, gas clouds, and powerful radiation. Unlike the relatively calm environment of our solar system, the galactic center is a place of extreme density. Stars are packed far more closely together than anywhere else in the galaxy. Distances that take light years to cross in our neighborhood are reduced to fractions of a light year here. This creates a crowded environment where gravitational interactions between stars are frequent and intense. Orbits are complex, and stars move at high speeds as they respond to the overwhelming gravitational pull of the central mass. At the very center of this region lies Sagittarius A, a supermassive black hole with a mass approximately 4 million times that of the Sunday. Despite its enormous mass, it occupies a region only about the size of our solar system. This means that a vast amount of matter is concentrated into an extremely small volume, creating a gravitational field so strong that not even light can escape from within its event horizon. Yet, paradoxically, this black hole is not a cosmic vacuum cleaner pulling everything into it. Instead, it influences its surroundings primarily through gravity, affecting the orbits of nearby stars without actively consuming everything around it. The presence of Sagittarius A times was confirmed through observations of stars orbiting an invisible point in space. These stars, known as S stars, move at incredibly high speeds as they trace tight orbits around the galactic center. Some of them reach velocities of thousands of kilometers per second, completing full orbits in just a few years. By tracking their motion over time, astronomers were able to calculate the mass of the unseen object at the center and conclude that it must be a supermassive black hole. One of the most famous of these stars is S2, which has provided some of the most precise measurements of the galactic center's properties. Its orbit brings it extremely close to Sagittarius A, allowing scientists to test predictions of general relativity in strong gravitational fields. During its closest approach, S2 moves at a significant fraction of the speed of light, experiencing extreme gravitational effects that slightly shift its orbit in ways that match Einstein's theory. Despite its power, Sagittarius A times is relatively quiet compared to black holes in other galaxies. It is not currently consuming large amounts of matter, which means it does not emit strong radiation from an active accretion disk. However, this does not mean it is inactive. Occasional flares of energy have been observed, likely caused by small amounts of gas or dust falling into the black hole and heating up as they spiral inward. These events provide valuable insights into the behavior of matter under extreme gravitational conditions. Surrounding the black hole is a complex environment of gas clouds, dust lanes, and star-forming regions. Some of the most massive and luminous stars in the galaxy are found near the center. These young stars emit intense radiation and powerful stellar winds, shaping the surrounding medium and influencing future star formation. The presence of both very old and very young stars in the same region reflects the long and dynamic history of the galactic center. The conditions in this region are unlike anything found in the outer parts of the galaxy. Temperatures are higher, radiation levels are stronger, and gravitational forces are far more intense. This makes the galactic center a natural laboratory for studying extreme physics. By observing how matter behaves in these conditions, scientists can test theories of gravity, stellar evolution, and black hole dynamics in ways that are impossible elsewhere. One of the most important discoveries about the galactic center is that it is not static. It is a dynamic environment where matter is constantly moving, interacting, and evolving. Gas clouds orbit the black hole, sometimes forming streams that spiral inward. Stars pass through dense regions, influencing each other's orbits through gravitational interactions. Over time, These processes shape the structure of the central region and contribute to the overall evolution of the galaxy. The motion of stars near the galactic center also provides evidence for the distribution of mass within the Milky Way. By studying their orbits, astronomers can map the gravitational field and determine how much mass is concentrated in different regions. These observations have confirmed that a large portion of the galaxy's mass is concentrated near the center, while the rest is distributed throughout the disk and halo. In addition to stars and gas, the galactic center is also a source of high-energy phenomena. X-ray emissions, gamma-ray bursts, and radio waves all originate from this region, indicating the presence of energetic processes occurring near Sagittarius A. Some of these emissions are produced when matter is heated to extreme temperatures as it falls toward the black hole, while others may be related to magnetic fields and particle acceleration. Despite the extreme conditions, the galactic center is not entirely hostile to structure. Stars continue to form in certain regions where gas densities are high enough to allow gravitational collapse. These star-forming regions are often embedded within large clouds of gas and dust, creating complex and visually striking structures when observed in infrared light. The study of the galactic center has also revealed evidence of past activity. Observations suggest that Sagittarius A times may have been more active in the past, possibly accreting larger amounts of matter and emitting stronger radiation. Remnants of this activity can still be seen in large-scale structures, such as gas bubbles and outflows, extending above and below the galactic plane. These features indicate that the center of the Milky Way has undergone periods of increased activity, followed by quieter phases. Understanding the galactic center is essential for understanding the Milky Way as a whole. The black hole at its core influences the motion of stars in the inner regions, shapes the distribution of gas, and contributes to the overall gravitational balance of the galaxy. Although it represents only a small fraction of the galaxy's total mass, its influence extends across thousands of light years. The relationship between Sagittarius A times and the rest of the galaxy is not one of domination, but of integration. The black hole is part of a larger system, interacting with its surroundings through gravity and energy exchange. It is both a product of the galaxy's evolution and a factor in its ongoing dynamics. As the galaxy changes over time, so too will the conditions at its center. Looking into the future, the galactic center will continue to evolve. Stars will orbit, gas will flow, and occasional interactions will occur between matter and the black hole. In the distant future, as the Milky Way merges with other galaxies, the central black hole may grow larger, eventually merging with the black hole of Andromeda when that galaxy collides with our own. This event will dramatically reshape the central region, creating an even more massive and energetic system. For now, however, the galactic center remains a place of mystery and discovery. It is hidden from direct view, but revealed through careful observation and advanced technology. Each new measurement brings us closer to understanding the forces at work in this extreme environment, shedding light on the role it plays in shaping the galaxy. In the end, the galactic center is a reminder that even within our own galaxy, there are regions that push the limits of our understanding. It shows us that the Milky Way is not uniform or simple, but a complex system with a dynamic core that influences everything around it. By studying this region, we gain insight not only into the nature of black holes and extreme physics, but also into the structure and evolution of the galaxy we call home. The Milky Way is not made of a single kind of star, but of an enormous and diverse population of stellar objects that reflect the full history of the galaxy. Every star carries information about the conditions in which it formed, the material it was made from, and the environment it has lived in over millions or billions of years. When we look at the galaxy as a whole, we are not just seeing points of light, we are seeing generations of stars, each representing a different chapter in cosmic evolution. Stars in the Milky Way are often grouped into broad categories based on their age, composition, and location. These groups are sometimes referred to as stellar populations. The oldest stars tend to be found in the galactic halo and the central bulge, while younger stars are concentrated in the spiral arms of the disk. This distribution tells a story of how the galaxy formed and evolved over time, gradually building up layers of complexity. The oldest stars in the Milky Way are thought to be nearly as old as the galaxy itself, formed more than 12 billion years ago. These ancient stars are typically found in globular clusters or in the halo. They are often low in heavy elements, meaning they were formed before successive generations of stars had enriched the galaxy with elements like carbon, oxygen, and iron. Because of this, they are sometimes referred to as metal-poor stars, even though they still contain small amounts of elements heavier than hydrogen and helium. These ancient stars are important because they preserve information about the early universe. They formed when the Milky Way was still in its infancy, a time when the galaxy was smaller, more chaotic, and less chemically evolved. By studying them, astronomers can learn about the conditions that existed shortly after the formation of the first galaxies. In a sense, they are living fossils that carry clues about the earliest stages of cosmic history. In contrast to these ancient stars, the disk of the Milky Way is home to much younger stellar populations. Here, new stars are constantly being formed in giant molecular clouds, regions of cold gas and dust that collapse under gravity. These young stars are often bright, hot, and massive, emitting large amounts of ultraviolet radiation that illuminates the surrounding nebulae where they were born. Young stars in the spiral arms are part of what is known as population 1 stars. These stars are relatively rich in heavy elements because they formed from material that had already been processed through earlier generations of stars. This enrichment is crucial for the formation of planets, as elements like silicon, iron, and oxygen are necessary for building rocky worlds. Our own Sun is part of this population, making it a relatively young star in cosmic terms, even though it is about 4.6 billion years old. The Sun is a yellow dwarf star, a stable and long-lived type of star that burns hydrogen in its core through nuclear fusion. It is neither very massive nor very small, placing it in a middle category that allows it to exist for billions of years. This stability has been essential for the development of life on Earth, as it provides a consistent energy source over long timescales. In addition to yellow dwarfs like the Sun, the Milky Way contains a wide range of other star types. Massive blue stars are among the most luminous and energetic objects in the galaxy. These stars burn through their fuel very quickly, living only a few million years before ending their lives in spectacular supernova explosions. Despite their short lifespans, they play a crucial role in shaping the galaxy by producing heavy elements and influencing their surroundings with intense radiation and stellar winds. Red dwarfs are the most common type of star in the Milky Way. These small, cool stars burn their fuel very slowly and can exist for trillions of years, far longer than the current age of the universe. Because of their long lifespans and low energy output, they are difficult to observe individually, but their sheer numbers make them a dominant component of the galaxy's stellar population. There are also many stars that exist in later stages of their evolution. Red giants are stars that have exhausted the hydrogen in their cores and expanded to enormous sizes. These stars are often hundreds of times larger than the Sun and emit large amounts of energy as they fuse heavier elements in their outer layers. Eventually, many of these stars shed their outer layers, creating beautiful planetary nebulae and leaving behind dense remnants such as white dwarfs. White dwarfs are the final stage for most stars like the Sunday. These objects are incredibly dense, with masses comparable to the Sun compressed into a volume similar to that of Earth. They no longer undergo nuclear fusion, and instead slowly cool over time, gradually fading into darkness over billions of years. Despite their small size, white dwarfs are extremely important for understanding stellar evolution and the long-term fate of stars. For more massive stars, the end of their life is far more dramatic. When these stars exhaust their nuclear fuel, they undergo a core collapse that leads to a supernova explosion. This event releases an enormous amount of energy, briefly outshining entire galaxies. The explosion disperses heavy elements into space, enriching the interstellar medium and contributing to the formation of new stars and planets. Depending on the mass of the original star, the remnant may become a neutron star or collapse further into a black hole. Neutron stars are among the most extreme objects in the universe. They are incredibly dense, with masses greater than the Sun, compressed into a sphere only about the size of a city. Their matter is so tightly packed that atoms are crushed together, forming a state of matter that cannot exist under normal conditions. Some neutron stars rotate rapidly and emit beams of radiation, known as pulsars, which can be detected as regular pulses of energy. Black holes represent the final stage of evolution for the most massive stars. Once formed, they create regions of space where gravity is so strong that nothing, not even light, can escape. While black holes themselves are invisible, their presence can be detected through their effects on nearby matter, such as stars orbiting an unseen object, or gas being heated as it falls inward. The diversity of stellar populations in the Milky Way reflects its long and complex history. The galaxy has been forming stars for more than 13 billion years, and during that time it has gone through many cycles of star formation and stellar death. Each generation of stars enriches the galaxy with heavier elements, gradually changing its chemical composition and enabling the formation of more complex structures. This process of chemical evolution is essential for the existence of planets and life. Early in the galaxy's history, there were very few heavy elements, meaning that rocky planets like Earth could not form. Over time, as stars lived and died, these elements became more abundant, allowing planetary systems to emerge. In this way, the history of stars is directly connected to the possibility of life within the galaxy. The distribution of stars in the Milky Way also reveals information about its structure and dynamics. Older stars tend to be found in the halo and bulge, while younger stars are concentrated in the disk and spiral arms. This pattern reflects the ongoing process of star formation in the galaxy's disk and the gradual accumulation of older populations in more stable regions. Star clusters provide additional insight into stellar populations. Open clusters are groups of young stars that formed together in the disk and remain loosely bound by gravity. Globular clusters, on the other hand, are much older and more tightly bound, containing some of the oldest stars in the galaxy. By studying these clusters, astronomers can trace the history of star formation across different regions and times. Variable stars also play an important role in understanding stellar populations. These stars change in brightness over time due to internal processes or external interactions. Certain types of variable stars can be used as distance indicators, helping astronomers measure the scale of the galaxy and beyond. This makes them valuable tools for mapping the structure of the Milky Way. Even though stars appear as fixed points of light in the night sky, they are constantly moving. Each star follows its own orbit around the galactic center, shaped by the combined gravitational influence of all the mass in the galaxy. Over long periods of time, this motion changes the arrangement of stars in the sky, although these changes are too slow to notice on human timescales. The study of stellar populations reveals that the Milky Way is not uniform but layered, with each layer representing a different epoch of formation. The halo contains the oldest stars, the disk contains younger generations, and the spiral arms are regions of active star formation. Together, these populations form a timeline of the galaxy's evolution, written in the distribution and properties of its stars. As we observe these stars, we are not just looking at distant objects. We are looking at the building blocks of the galaxy, each one contributing to its structure, history, and future. The diversity of stars in the Milky Way reflects the diversity of processes that have shaped it over billions of years. In the end, stellar populations are more than just categories of stars. They are a record of cosmic history, showing how the galaxy has changed from a simple collection of primordial gas into a rich and complex system. By studying them, we gain insight into the life cycle of matter in the universe and our own place within that ongoing story. Within the vast structure of the Milky Way, there are regions where the cycle of creation is actively unfolding. These are places where gas and dust, once scattered and diffuse, come together under the force of gravity to form new stars. They are not quiet or static environments, but dynamic and often turbulent regions where energy, pressure, and motion interact in complex ways. These stellar nurseries are known as nebulae, and they represent one of the most fundamental processes in the galaxy, the birth of stars. Nebulae are vast clouds of interstellar material composed primarily of hydrogen, along with helium and trace amounts of heavier elements. They exist throughout the galactic disk, often concentrated in spiral arms where the density of gas is higher. While some nebulae are relatively small on a galactic scale, others span hundreds of light-years, containing enough material to form thousands of stars. Despite their size, they are extremely diffuse, with densities far lower than anything we experience on Earth. The process of star formation begins when a region within a nebula becomes unstable. This instability can be triggered by several factors, including shock waves from nearby supernovae, collisions between gas clouds, or gravitational interactions within the galaxy. When such a disturbance occurs, parts of the cloud begin to collapse under their own gravity. As the material contracts, it becomes denser and hotter, gradually forming clumps that continue to grow over time. As these clumps collapse further, they begin to fragment into smaller regions, each of which may eventually form a star. This fragmentation is an important part of the process, as it leads to the formation of star clusters rather than isolated stars. Within a single nebula, many stars can form at once, all originating from the same cloud of material but evolving independently once they are born. As the collapsing material becomes denser, the center of each clump heats up due to gravitational compression. This heating continues until the temperature and pressure at the core become high enough to ignite nuclear fusion. At this point, hydrogen atoms begin to fuse into helium, releasing enormous amounts of energy. This marks the birth of a new star, a moment when gravity and nuclear physics reach a balance that allows the star to stabilize and begin its long life. Before this ignition occurs, the object is known as a protostar. Protostars are still in the process of formation and are often surrounded by rotating disks of gas and dust. These disks are remnants of the original cloud and play an important role in the formation of planetary systems. As material in the disk continues to orbit the young star, it can clump together to form larger bodies, eventually leading to the creation of planets, moons, and other objects. During the early stages of star formation, the protostar is often hidden from visible light by thick clouds of dust. However, it can be observed in infrared wavelengths, which are able to penetrate the surrounding material. These observations reveal complex structures within nebulae, including filaments, pillars, and dense cores where stars are actively forming. One of the most famous examples of a stellar nursery is the Orion Nebula, a region located in one of the Milky Way's spiral arms. This nebula is visible to the naked eye under dark skies and has been studied extensively by astronomers. It contains hundreds of young stars, along with dense clouds of gas where new stars are still forming. The energy emitted by these young stars illuminates the surrounding gas, creating a glowing cloud that can be seen across vast distances. Nebulae are not uniform in appearance. Some are bright and colorful, glowing due to ionization caused by nearby stars. These are known as emission nebulae. Others are dark, appearing as silhouettes against brighter backgrounds. These dark nebulae are regions where dense clouds of dust block light from objects behind them, revealing the structure of the interstellar medium. There are also reflection nebulae, which shine by reflecting the light of nearby stars, rather than producing their own light. The formation of stars within nebulae is not a rapid process. It can take millions of years for a cloud to fully collapse and produce a stable star. Even after a star has formed, the surrounding material may continue to accrete onto it or form additional stars nearby. This extended timescale means that star formation is a continuous process in the galaxy, occurring in different regions at different times. As new stars form, they begin to influence their surroundings. Young, massive stars emit large amounts of ultraviolet radiation, which can ionize nearby gas and create expanding bubbles within the nebula. These bubbles can compress surrounding material, potentially triggering the formation of additional stars. In this way, star formation can become a self-propagating process, where the birth of one generation of stars leads to the creation of another. However, star formation is also self-limiting. As stars form and begin to emit radiation and stellar winds, they gradually disperse the remaining gas in the nebula. Over time, this feedback process clears out the region, stopping further star formation in that particular cloud. The newly formed stars are then left behind as an open cluster, slowly drifting apart due to gravitational interactions. The efficiency of star formation in a nebula is relatively low. Only a small fraction of the available gas is converted into stars, while the rest is dispersed back into the interstellar medium. This inefficiency is an important factor in the long-term evolution of galaxies, as it regulates the rate at which new stars are formed and ensures that star formation does not consume all available material too quickly. Over time, the material expelled by stars through winds and supernova explosions enriches the interstellar medium with heavier elements. These elements are essential for the formation of planets and complex chemistry. Without this enrichment, later generations of stars would lack the ingredients needed to form rocky worlds and potentially life-supporting environments. The cycle of star formation and destruction is therefore central to the evolution of the Milky Way. Nebulae serve as the starting point of this cycle, collecting material from previous generations of stars and transforming it into new ones. This continuous recycling of matter ensures that the galaxy remains active and evolving over billions of years. In some regions of the galaxy, star formation occurs at a much higher rate than average. These regions are known as star-forming regions or starburst regions. They are often triggered by large-scale events such as the collision of gas clouds or interactions with other galaxies. In these environments, hundreds or even thousands of stars can form in a relatively short period of time, leading to intense bursts of activity. At the other extreme, there are regions where star formation has largely ceased. In these areas, the available gas has been used up or dispersed, leaving behind older stellar populations. These regions gradually become more stable and less active, contributing to the long-term aging of the galaxy. The study of nebulae also provides insight into the formation of planetary systems. The same disks of gas and dust that surround young stars can give rise to planets through a process of accretion. Small particles collide and stick together, gradually forming larger and larger bodies. Over time, these bodies can grow into planets, moons, and other objects that orbit the central star. This process suggests that planetary systems are a natural byproduct of star formation. As a result, planets may be extremely common in the Milky Way, forming around many of the stars born in nebulae. This has important implications for the possibility of life elsewhere in the galaxy, as it increases the number of potential environments where life could develop. The connection between nebulae and stellar evolution also highlights the interconnected nature of the galaxy. Material is constantly being recycled between stars and the interstellar medium. Stars form from gas clouds, live their lives, and then return material back into space through stellar winds or explosive deaths. This material then becomes the raw material for new stars, continuing the cycle. Even though nebulae are regions of creation, they are also shaped by destruction. Supernova explosions from nearby massive stars can compress or disperse gas clouds, altering their structure and triggering new waves of star formation. In this way, death and creation are closely linked processes within the galaxy. From a broader perspective, nebulae represent one of the key mechanisms through which the Milky Way evolves over time. They are the sites where the galaxy renews itself, transforming old material into new generations of stars. Without this process, the galaxy would slowly run out of active stars and become a cold, static system dominated by remnants. Instead, the presence of nebulae ensures that the Milky Way remains dynamic. Even after billions of years, it continues to produce new stars, maintain its structure, and evolve in response to internal and external forces. This ongoing cycle is one of the defining features of spiral galaxies like our own. As we observe nebulae across the galaxy, we are witnessing the earliest stages of stellar life. These regions show us where stars come from, how they are formed, and how they contribute to the larger structure of the Milky Way. They are not just beautiful cosmic clouds, but active environments where the future of the galaxy is being shaped. In the end, nebulae represent the beginning of the stellar journey. They are the places where gravity gathers matter, where energy builds, and where new stars ignite. Through them, we see the continuous cycle of creation that defines the Milky Way, linking past generations of stars to those yet to come, and ensuring that the galaxy remains alive with activity across cosmic time. Within the Milky Way, the formation of stars is only part of a much larger story. Around many of these stars, new worlds are being built in silence, shaped by the same processes that formed the stars themselves. These worlds begin as tiny particles of dust and ice orbiting young stars in swirling disks of material. Over time, they collide, stick together, and grow into planets, moons, and other bodies that form complete planetary systems. This process is not rare or exceptional. It appears to be a natural outcome of star formation itself, suggesting that planets are a common feature throughout our galaxy. For most of human history, we assumed that planets existed only in our own solar system. The idea of other worlds orbiting distant stars was purely speculative. It was only in recent decades that we gained the ability to detect planets beyond our solar system, known as exoplanets. Since then, thousands of these distant worlds have been discovered, revealing that planetary systems are not unique to our own, but are widespread throughout the Milky Way. The formation of planets begins in the same environments where stars are born. When a nebula collapses under gravity to form a protostar, not all of the material falls directly into the star. Instead, some of it flattens into a rotating disk around the young star. This disk, known as a protoplanetary disk, is made of gas and dust that continues to orbit the star as it evolves. Within this disk, the raw ingredients for planets are present. In the early stages, the disk is hot and chaotic. Small dust grains collide and begin to stick together due to electrostatic forces. Over time, these grains grow into larger clumps called planetesimals. These planetesimals continue to collide and merge, gradually forming larger bodies. The process is slow and complex, driven by gravity, collisions, and interactions within the disk. As these bodies grow, their gravity becomes stronger, allowing them to attract more material. This leads to a runaway process where larger objects grow faster than smaller ones, eventually forming protoplanets. Depending on their location within the disk, these protoplanets can develop into different types of planets. Close to the star, where temperatures are high, rocky planets tend to form. Farther out, where temperatures are lower, gas and ice giants can develop. This distribution is influenced by the composition of the disk itself. In the inner regions, only materials with high melting points can survive, such as metals and silicates. These materials form dense, rocky planets like Earth and Mars. In the outer regions, volatile compounds like water, ammonia, and methane can freeze, allowing the formation of larger cores that can attract thick atmospheres of hydrogen and helium. The result is a diverse range of planetary systems. Some systems contain large gas giants close to their stars, while others have compact systems of rocky planets. Some systems appear stable and orderly, while others show evidence of past migration and orbital rearrangement. This diversity reflects the complex and often chaotic nature of planet formation. Our own solar system is just one example of this process. It contains a mix of rocky inner planets and gas giants in the outer regions. The presence of Earth in the so-called habitable zone, where temperatures allow liquid water to exist, is one of the key factors that made life possible. However, observations of exoplanets have shown that such configurations are not unique. Many stars in the Milky Way host planets within their habitable zones, suggesting that potentially life-supporting environments may be common. The discovery of exoplanets has transformed our understanding of the galaxy. Using methods such as the transit method and radial velocity measurements, astronomers have identified thousands of planets orbiting distant stars. The transit method detects small dips in a star's brightness when a planet passes in front of it, while radial velocity measurements detect the slight wobble of a star caused by the gravitational pull of an orbiting planet. These techniques have revealed a surprising variety of worlds. Some exoplanets are massive gas giants orbiting very close to their stars, known as hot Jupiters. Others are small, rocky planets, similar in size to Earth. Some are located in multi-planet systems, while others appear to be solitary. This variety suggests that planet formation is a flexible process that can produce a wide range of outcomes. One of the most important discoveries in exoplanet research is that planets are extremely common. Observations suggest that most stars in the Milky Way host at least one planet, and many host multiple planets. This means that there are likely billions of planets in our galaxy alone. Among these, a significant number may be located in conditions suitable for liquid water, increasing the possibility of habitable environments. The study of exoplanets also reveals that planetary systems can be very different from our own. In some systems, planets orbit very close to their stars, completing an orbit in just a few days. In others, planets have highly elliptical or tilted orbits. These variations suggest that planetary systems are shaped by a combination of initial conditions and later dynamical interactions, including migration and gravitational perturbations. Planetary migration is an important process in many systems. After forming, planets do not always remain in the positions where they were born. Interactions with the surrounding disk can cause them to move inward or outward over time. This migration can significantly alter the architecture of a planetary system, sometimes bringing large planets close to their stars or reshaping the orbits of smaller planets. In addition to gas and rocky planets, some systems may also contain moons, asteroid belts, and comets. These smaller bodies play an important role in the evolution of planetary systems. They can deliver water and organic materials to rocky planets, potentially contributing to the development of life. In our own solar system, comets and asteroids are thought to have played a role in delivering water to early Earth. The habitability of a planet depends on many factors beyond just its distance from its star. The composition of its atmosphere, the presence of magnetic fields, geological activity, and the stability of its orbit all influence whether conditions are suitable for life. Even within the habitable zone, not all planets will be capable of supporting life as we know it. Despite this complexity, the sheer number of planets in the Milky Way increases the likelihood that some of them could host life. Even if life is rare, the vast number of potential environments makes it statistically possible that it exists elsewhere in the galaxy. This idea has driven much of the modern search for extraterrestrial life, focusing on planets that resemble Earth in size, temperature, and composition. The study of planetary systems also provides insight into the history of the galaxy itself. Since planets form alongside stars, their distribution reflects the chemical evolution of the Milky Way. Early in the galaxy's history, heavy elements were scarce, limiting the formation of rocky planets. As generations of stars lived and died, these elements became more abundant, allowing more complex planetary systems to form. This means that planetary systems in different parts of the galaxy may have different characteristics depending on their age and location. Older regions of the galaxy may have fewer rocky planets, while younger, metal-rich regions may have more diverse planetary systems. This connection between stellar evolution and planet formation highlights the interconnected nature of galactic processes. The discovery of exoplanets has also changed our perspective on the uniqueness of our solar system. While it was once thought to be a typical example, we now know that it may be only one of many possible configurations. Some aspects of our system, such as the presence of large gas giants in the outer regions that help stabilize inner orbits, may even be relatively uncommon. As technology continues to improve, future observations will allow us to study exoplanet atmospheres in greater detail. By analyzing the light that passes through or reflects off these atmospheres, scientists can search for chemical signatures that might indicate biological activity. This includes gases such as oxygen, methane, or carbon dioxide in specific combinations that are difficult to explain through purely geological processes. These studies are still in their early stages, but they represent one of the most exciting frontiers in astronomy. The possibility of detecting signs of life beyond Earth would fundamentally change our understanding of the universe and our place within it. Even if such signs are not found, the process of exploring exoplanets will continue to reveal the diversity and complexity of planetary systems throughout the Milky Way. In the end, planetary systems are a natural extension of star formation. They emerge from the same processes that create stars, shaped by gravity, motion, and the distribution of material within the galaxy. Each system represents a small but significant part of the Milky Way's ongoing evolution. As we look at the night sky, it is important to remember that many of the stars we see are likely surrounded by planets. Each of these systems is a potential world, shaped by the same physical laws that govern our own. Together, they form a vast network of planetary systems scattered throughout the galaxy, each with its own history, structure, and possibilities. The study of these worlds continues to expand our understanding of the Milky Way. It shows us that the galaxy is not just a collection of stars, but a complex system of stars and planets, all interacting and evolving together. In this way, the search for exoplanets is also a search for context, helping us understand where we fit within the broader structure of the cosmos. The Milky Way is not a static structure suspended in space. It is a vast rotating system in motion, shaped by gravity, momentum, and the invisible influence of dark matter. Every star, cloud of gas and cluster of matter is in motion, following orbits that trace the gravitational field of the galaxy as a whole. To understand the Milky Way fully, we must understand how it moves, how it rotates, and how that motion shapes its structure over time. At first glance, it might seem natural to assume that the galaxy rotates like a solid object, with all parts moving together in a single rigid motion. However, this is not the case. The Milky Way exhibits what is known as differential rotation. This means that different parts of the galaxy rotate at different speeds depending on their distance from the center. Stars closer to the galactic center orbit much faster than those farther out, while the outer regions move more slowly in a gradual sweep around the galaxy. This type of motion is very different from the rotation of a solid disk. In a solid object, all parts complete a rotation in the same amount of time. In the Milky Way, however, orbital periods vary dramatically. The Sun, located about 26,000 light-years from the center, takes roughly 225 to 250 million years to complete one orbit around the galaxy. Closer to the center, stars complete their orbits much more quickly, while stars in the outer disk take significantly longer. This differential rotation has profound effects on the structure of the galaxy. One of the most important consequences is the formation and maintenance of spiral arms. These arms are not fixed structures made of the same stars over time. Instead, they are regions of higher density that move through the disk like waves. As gas and stars orbit the center, they pass through these density waves temporarily slowing down and becoming more concentrated in these regions. This process is similar to traffic on a highway. Individual cars move through areas of congestion, but the congestion itself can remain in place and even move slowly along the road. In the galaxy, spiral arms are the regions where matter becomes compressed, leading to increased star formation. As a result, these arms appear brighter and more active than the surrounding regions, even though the stars within them are constantly changing. The motion of the Milky Way is governed primarily by gravity. Every object in the galaxy feels the combined gravitational pull of all other objects, from nearby stars to distant clusters and the large-scale distribution of dark matter. This creates a complex gravitational field that determines how everything moves. Stars do not orbit a single dominant center in a simple way. Instead, they respond to the overall mass distribution of the galaxy. At the center of the Milky Way, the gravitational influence is dominated by the supermassive black hole Sagittarius A, but its effect on the overall rotation of the galaxy is relatively small compared to the total mass of stars and dark matter. Most of the galaxy's rotational behavior is determined by the combined mass of the disk and the extended halo of dark matter that surrounds it. One of the key discoveries in understanding galactic motion came from studying rotation curves. A rotation curve shows how the orbital speed of stars changes with distance from the center of the galaxy. Based on visible matter alone, one would expect the outer stars to move more slowly as distance increases. However, observations of the Milky Way and other galaxies show that orbital speeds remain unexpectedly high even at large distances from the center. This discrepancy led to one of the most important conclusions in modern astrophysics: the existence of dark matter. Dark matter does not emit or absorb light, making it invisible to direct observation. However, its gravitational effects are clearly visible in the motion of stars and gas. The flat rotation curve of the Milky Way indicates that there is far more mass present than what we can see, distributed in a vast halo that extends far beyond the visible disk. The dark matter halo plays a crucial role in stabilizing the galaxy. Without it, the outer regions of the Milky Way would not have enough gravitational support to maintain their observed speeds. Stars in the outer disk would drift away, and the galaxy would not hold together in its current form. Instead, the dark matter halo provides an extended gravitational framework that binds the galaxy together across enormous distances. The motion of stars within the galaxy is not limited to simple circular orbits. Many stars follow slightly elliptical paths, moving closer and farther from the galactic center over time. These orbits are influenced by local gravitational interactions, including encounters with other stars, molecular clouds, and spiral arms. As a result, the motion of individual stars is complex, even though the overall structure of the galaxy remains relatively stable. In addition to orbital motion around the center, the Milky Way itself is also moving through space. It is part of a larger system known as the Local Group, which includes the Andromeda Galaxy, the Triangulum Galaxy, and numerous smaller dwarf galaxies. The Milky Way and Andromeda are currently moving toward each other at a speed of about 110 kilometers per second. This motion is driven by their mutual gravitational attraction and will eventually lead to a collision and merger in several billion years. The motion of the Milky Way within the local group is influenced not only by gravity, but also by the expansion of the universe. On very large scales, space itself is expanding, causing distant galaxies to move away from each other. However, within gravitationally bound systems like the local group, gravity dominates over expansion, allowing galaxies to move toward each other rather than being carried apart. The interplay between expansion and gravity creates a layered structure of motion in the universe. On small scales, such as within solar systems, gravity dominates completely. On intermediate scales, such as within galaxies, gravity still holds systems together, but with complex internal motion. On the largest scales, expansion becomes dominant, shaping the distribution of galaxy clusters and superclusters. Within the Milky Way, the motion of gas plays a particularly important role in shaping the galaxy's structure. Gas clouds respond to both gravity and pressure forces, allowing them to flow through the disk and concentrate in certain regions. As these clouds move through spiral arms, they are compressed, triggering bursts of star formation. This process links the motion of the galaxy directly to the creation of new stars. Magnetic fields also influence the motion of charged particles within the interstellar medium. While they are weak compared to gravity, they can guide the flow of ionized gas and affect the structure of nebulae and star-forming regions. These fields are shaped by the overall motion of the galaxy and, in turn, contribute to the complexity of gas dynamics. The motion of the Milky Way is not constant over time. It evolves as the galaxy interacts with its environment. Encounters with smaller galaxies can distort its disk, create streams of stars, and trigger waves of star formation. These interactions leave behind visible traces that persist for billions of years, recording the history of the galaxy's movement through space. One example of this is the Sagittarius dwarf galaxy, a smaller galaxy currently being absorbed by the Milky Way. As it orbits and gradually disintegrates, it leaves behind streams of stars that wrap around the galaxy. These stellar streams provide evidence of past and ongoing interactions, showing that the Milky Way is still growing through the accretion of smaller systems. The overall motion of the galaxy is also influenced by its internal structure. The distribution of mass in the disk, bulge, and halo determines how different regions respond to gravitational forces. Changes in this distribution over time can subtly alter the rotation and shape of the galaxy. Although these changes occur slowly, they accumulate over billions of years, contributing to the long-term evolution of the Milky Way. From our perspective on Earth, the motion of the galaxy is largely imperceptible on human timescales. The Sun moves through space at about 220 kilometers per second, yet this motion is not felt in any direct way. The night sky appears stable because the relative positions of nearby stars change very slowly. However, over millions of years, the structure of the sky does change significantly as stars move along their orbits around the galactic center. In the distant past and future, the appearance of the Milky Way from Earth would be very different. Stars that are currently visible will shift positions, new stars will come into view, and the structure of the constellations will gradually transform. This slow but constant change reflects the underlying motion of the galaxy itself. The study of galactic motion also provides insight into fundamental physics. By analyzing how stars move, astronomers can test theories of gravity on large scales and investigate the distribution of dark matter. These studies have confirmed that Newtonian gravity and general relativity both play important roles in describing the dynamics of the Milky Way, while also revealing areas where additional components, such as dark matter, are required. Ultimately, the motion of the Milky Way is a reflection of the balance between gravity, momentum, and cosmic expansion. It is a system in constant motion, yet stable over long periods of time. Stars orbit, gas flows, and structures evolve, but the overall shape of the galaxy persists. In understanding this motion, we gain a deeper appreciation of the Milky Way as a living system. It is not a static collection of stars, but a dynamic and evolving structure shaped by forces that operate across unimaginable scales. Every orbit, every spiral arm, and every movement of gas contributes to the ongoing story of the galaxy. As we observe this motion from within, we are both participants and observers. Our solar system is carried along within the flow of the galaxy, completing its own orbit, while the Milky Way continues its journey through space. In this sense, we are part of a vast cosmic dance, one that has been unfolding for billions of years and will continue long into the future. Hidden within the visible structure of the Milky Way is something that cannot be seen directly, yet reveals itself through its influence on everything we observe. It does not emit light, it does not absorb radiation in any ordinary way, and it does not interact with matter through electromagnetic forces. And yet, without it, the galaxy would fall apart. This unseen component is known as dark matter, and it forms one of the most important and mysterious parts of the Milky Way. When we look at the night sky, we see stars, glowing gas clouds, and distant galaxies. All of these are made of ordinary matter, the same kind of material that makes up planets, people, and everything familiar in the universe. This matter interacts with light, which is why we can see it. But when astronomers began measuring how galaxies move, they discovered something unexpected. The visible matter was not enough to explain the motion of stars, especially in the outer regions of galaxies. Something else had to be present, something invisible but massive. In the Milky Way, this mystery becomes clear when we study how stars orbit the galactic center. Based on the amount of visible matter, we would expect stars farther from the center to move more slowly, since there is less gravitational pull from the inner regions. However, observations show that stars in the outer parts of the galaxy move much faster than expected. Their speeds remain relatively constant, even at great distances from the center. This flat rotation curve is one of the strongest pieces of evidence that dark matter exists. To explain this behavior, scientists propose that the Milky Way is surrounded by a vast halo of dark matter. This halo extends far beyond the visible disk of the galaxy, forming a massive spherical distribution of unseen mass. While we cannot detect dark matter directly, its gravitational influence affects the motion of stars, gas clouds, and even entire galaxies. It is this influence that holds the Milky Way together, preventing it from flying apart under its own rotation. The dark matter halo is not concentrated in one place. Instead, it forms a diffuse but massive structure that envelops the entire galaxy. It is much larger than the visible disk, extending hundreds of thousands of light-years in all directions. In fact, most of the mass of the Milky Way is thought to be in this halo rather than in the stars and gas we can see. This means that the galaxy we observe is only a small part of a much larger invisible structure. One of the most important characteristics of dark matter is that it does not interact with light. This means it neither emits, absorbs, nor reflects electromagnetic radiation. As a result, it cannot be observed using traditional telescopes. Its presence is inferred entirely through gravity. When scientists map the motion of stars and galaxies, they find that there must be far more mass present than what is visible. This missing mass is attributed to dark matter. The concept of dark matter was not introduced lightly. It emerged gradually through a series of observations that could not be explained by visible matter alone. One of the earliest clues came from the study of galaxy clusters, where galaxies were moving too quickly to be held together by the gravity of visible material. Later, measurements of individual galaxies, including the Milky Way, confirmed that this discrepancy was not an isolated case, but a widespread phenomenon. In the Milky Way, dark matter plays a crucial role in shaping the structure and dynamics of the galaxy. Without it, the outer stars would not have enough gravitational support to maintain their orbits. The galaxy would not remain stable over billions of years. Instead, it would slowly disperse. Dark matter provides the additional gravitational force needed to keep everything bound together, acting as an invisible scaffold that supports the visible structure. Despite its importance, the nature of dark matter remains unknown. It does not fit into the standard model of particle physics, which describes all known fundamental particles and forces. This has led scientists to propose a variety of possibilities for what dark matter might be. Some theories suggest that it is made of new types of particles that interact only through gravity and possibly weak nuclear forces. Others propose more exotic explanations, such as modifications to the laws of gravity itself. One of the leading candidates for dark matter is a class of particles known as weakly interacting massive particles, or WIMPs. These hypothetical particles would be heavy but interact very weakly with ordinary matter, making them extremely difficult to detect. Another possibility involves axions, very light particles, that could also account for some of the missing mass in the universe. Despite extensive searches, however, no direct detection of dark matter particles has yet been confirmed. The challenge of detecting dark matter lies in its very nature. Since it does not interact with light, it cannot be observed using telescopes. Instead, scientists attempt to detect it through indirect methods, such as looking for rare interactions between dark matter particles and ordinary matter in highly sensitive detectors placed deep underground. Other experiments search for signs of dark matter production in high-energy particle collisions, such as those conducted in particle accelerators. In addition to direct detection efforts, astronomers also study the effects of dark matter on large-scale structures. Computer simulations of galaxy formation that include dark matter are able to reproduce the observed distribution of galaxies and clusters in the universe. Without dark matter, these simulations fail to match reality. This provides further evidence that dark matter is a real and essential component of the cosmos. In the Milky Way, the dark matter halo influences not only the motion of stars, but also the formation of the galaxy itself. In the early universe, small fluctuations in the density of dark matter acted as seeds for the formation of larger structures. Ordinary matter was drawn into these gravitational wells, eventually forming stars and galaxies. In this way, dark matter played a fundamental role in shaping the large-scale structure of the universe. The distribution of dark matter in the Milky Way is not perfectly uniform. It is thought to form a roughly spherical halo, but with possible clumps and substructures. These variations can influence the motion of stars and the behavior of satellite galaxies. Some small galaxies orbiting the Milky Way may be dominated almost entirely by dark matter, making them particularly important for studying its properties. Although dark matter does not interact with light, it does interact with gravity in the same way as ordinary matter. This means that it can bend light through gravitational lensing, an effect where the gravity of a massive object distorts the path of light from more distant sources. Observations of gravitational lensing in galaxies and clusters provide additional evidence for the presence of dark matter and help map its distribution. The idea that most of the Milky Way is invisible is both surprising and profound. It means that the galaxy we see is only a small fraction of the total structure. The stars, gas, and dust that make up the visible disk are embedded within a much larger halo of unseen mass. This hidden component shapes the motion of everything we observe, even though it cannot be seen directly. Understanding dark matter is one of the central challenges in modern astrophysics. It connects the study of galaxies, particle physics, and cosmology. It raises questions about the fundamental nature of matter and the forces that govern the universe. Despite decades of research, it remains one of the most important unsolved problems in science. In the Milky Way, the effects of dark matter are everywhere, even if we cannot see it. It determines how fast stars orbit the center, how the galaxy holds together, and how it interacts with other galaxies. Without it, the Milky Way as we know it would not exist. Its presence is not optional but essential to the structure of the galaxy. The study of dark matter also highlights an important aspect of scientific discovery. Some of the most significant components of the universe are not directly visible. They are revealed only through their effects on other things. This means that understanding the universe requires not only observation, but also inference, modeling, and careful interpretation of indirect evidence. As research continues, new experiments and observations may eventually reveal the true nature of dark matter. Whether it is composed of new particles, exotic physics, or something entirely unexpected, its discovery would fundamentally change our understanding of the universe. Until then, it remains one of the most powerful and mysterious influences in the Milky Way. In the end, dark matter reminds us that what we see is not always what exists. The Milky Way is far more than its visible stars and glowing clouds. It is embedded in a vast, invisible structure that shapes its motion, its formation, and its fate. By studying this hidden component, we come closer to understanding the true nature of our galaxy and the universe beyond it. The Milky Way is not an isolated island in space. It is part of a much larger environment where galaxies interact, collide, and merge over immense stretches of time. While the galaxy may appear stable and unchanging on human timescales, its history is filled with violent encounters and gradual assimilations of smaller systems. These processes continue today and will shape the future of our galaxy in profound ways. To understand the future of the Milky Way, we must first understand its past interactions. Over billions of years, the Milky Way has grown by absorbing smaller dwarf galaxies. These smaller systems, containing their own stars, gas, and dark matter, have been pulled in by the gravitational influence of our galaxy. As they approach, they are stretched, distorted, and eventually torn apart in a process known as tidal disruption. When a dwarf galaxy is captured by the Milky Way, it does not immediately disappear. Instead, it is gradually pulled apart as its stars are scattered along its orbit. These stars form long, thin structures known as stellar streams, which wrap around the galaxy like faint ribbons of light. Although difficult to observe, these streams are powerful evidence of past galactic mergers. One of the most significant examples of this process is the Sagittarius dwarf galaxy, a small galaxy currently being absorbed by the Milky Way. As it orbits our galaxy, it is slowly disintegrating under tidal forces. Its stars are being stripped away and distributed along a vast stream that encircles the Milky Way. This ongoing event provides a real-time example of how galaxies grow through accretion. These interactions are not rare or exceptional. They are a fundamental part of how galaxies evolve. The Milky Way has likely merged with dozens, if not hundreds, of smaller galaxies throughout its history. Each merger adds new stars, gas, and dark matter to the galaxy, gradually increasing its size and complexity. In this way, the Milky Way is a product of many smaller systems that have been combined over time. While minor mergers with dwarf galaxies are ongoing, the most significant future event for the Milky Way is its impending collision with the Andromeda galaxy. Andromeda is the largest galaxy in the local group and is currently moving toward the Milky Way at a speed of about 110 kilometers per second. This motion is driven by mutual gravitational attraction between the two galaxies. Despite the enormous distances involved, this collision is inevitable on cosmic timescales. In approximately 4 to 5 billion years, the Milky Way and Andromeda will begin to interact directly. At first, their outer regions will overlap, and gravitational forces will begin to distort their shapes. Stars will be pulled into new orbits, and gas clouds will be compressed, triggering bursts of star formation. It is important to understand that although this event is often described as a collision, the distances between individual stars are so large that direct stellar collisions will be extremely rare. Instead, the galaxies will pass through each other, with their gravitational fields interacting in complex ways. The result will be a gradual merging of two massive systems into a single, larger galaxy. During this process, the structure of both galaxies will be dramatically altered. Spiral arms will be disrupted, Tidal tails of stars will be flung into space, and vast regions of gas will be compressed. These compressions will likely lead to intense periods of star formation, creating what is known as a starburst phase. In this phase, the rate of new star formation can increase significantly compared to normal conditions. As the merger continues, the individual identities of the Milky Way and Andromeda will begin to fade. Their disks will become distorted, and their stars will mix into a single, more diffuse structure. Over time, the two galaxies will settle into a new equilibrium, forming a large elliptical galaxy. This future galaxy is sometimes referred to as Milkomeda or Milkdromeda. The transformation from spiral galaxies to an elliptical galaxy is a natural outcome of major mergers. Spiral structure depends on relatively stable rotating disks of gas and stars. When two large galaxies collide, these ordered structures are disrupted. The resulting system is more random and spheroidal, with stars moving in a wide range of orbits rather than a coherent rotating disk. The Milky Way is not unique in this process. Observations of distant galaxies show that mergers are common throughout the universe. Many of the large elliptical galaxies we see today are likely the result of past collisions between spiral galaxies. These events are an essential part of galactic evolution and play a major role in shaping the large-scale structure of the universe. In addition to the future collision with Andromeda, the Milky Way continues to interact with smaller satellite galaxies today. The Large and Small Magellanic Clouds, for example, are two irregular dwarf galaxies that orbit the Milky Way and are gradually being influenced by its gravity. Over time, they may also be partially or fully absorbed into the galaxy. These satellite interactions contribute to the growth and evolution of the Milky Way. As they are disrupted, they supply new material to the galaxy, including gas that can fuel star formation. They also contribute to the complexity of the galaxy's halo, adding streams of stars and dark matter that reflect their original structure. The future of the Milky Way is therefore one of continuous change. Even before the major merger with Andromeda, the galaxy will continue to evolve through smaller interactions and internal processes. Star formation will continue in the spiral arms, stars will age and die, and the distribution of gas and dust will shift over time. Eventually, however, the most dramatic transformation will come from the merger with Andromeda. When this event occurs, the night sky, as seen from Earth, will change dramatically. The Andromeda galaxy is already visible as a faint smudge of light in the night sky, but during the early stages of the collision, it will grow larger and brighter. Over time, it will dominate the sky, appearing as a vast structure filled with stars. As the merger progresses, the structure of the sky will become increasingly complex. Streams of stars will stretch across the sky, and the overall pattern of the Milky Way band will be disrupted. Eventually, as the galaxies fully merge, the familiar structure of the Milky Way will disappear entirely, replaced by a new galactic system. It is important to note that the solar system itself is not expected to be destroyed in this process. While its position within the galaxy may change significantly, the vast distances between stars mean that the likelihood of direct collisions is extremely low. Instead, the solar system will likely be moved into a new orbit within the merged galaxy, possibly farther from the center than its current position. Over even longer timescales, the merged galaxy will continue to evolve. Star formation will gradually slow as gas reserves are used up or expelled. The galaxy will become more stable and less active, dominated by older stars. This is the natural end state of many large galaxies, where the available material for new star formation becomes increasingly scarce. However, even in this distant future, the galaxy will not be completely static. Small interactions with remaining satellite galaxies will continue, and occasional internal processes will still occur. Black holes at the centers of galaxies may grow through slow accretion or future mergers with other black holes, releasing energy in the process. The study of galactic collisions provides important insight into the long-term evolution of the universe. It shows that galaxies are not permanent structures, but evolving systems shaped by gravity and time. The Milky Way itself is the result of many past mergers, and its future will be defined by new ones. These processes also help explain the diversity of galaxies we observe today. Spiral galaxies, elliptical galaxies, and irregular galaxies are not fixed categories, but different stages or outcomes of galactic evolution. A spiral galaxy like the Milky Way can become an elliptical galaxy after a major merger, while interactions can also transform smaller systems into irregular shapes. The future collision between the Milky Way and Andromeda is one of the most well-studied events in cosmic evolution. Computer simulations allow scientists to model how the galaxies will interact over billions of years. These simulations show the gradual merging process, the formation of tidal structures, and the eventual stabilization of the final galaxy. While the timescales involved are far beyond human experience, the physical processes are well understood. Gravity drives the interaction. Gas dynamics shapes star formation, and orbital motion determines the final structure. These same principles operate across the universe, making galactic collisions a universal phenomenon. In the end, the story of galactic collisions is the story of growth through interaction. The Milky Way has not always existed in its current form, and it will not remain as it is forever. It is part of a larger cosmic cycle in which galaxies form, interact, merge, and evolve over billions of years. The future merger with Andromeda is not an ending, but a transformation. It represents the next stage in the life of our galaxy, where two massive systems become one. Through this process, the Milky Way will change in structure, appearance, and dynamics, continuing its journey through cosmic time as part of an ever-evolving universe. When we step back and view the Milky Way in its largest context, it becomes clear that our galaxy is not an isolated structure, but part of an immense cosmic network. It is one member of a small collection of galaxies known as the local group, which itself is part of even larger structures that stretch across the universe in a vast, interconnected web. Understanding the Milky Way's place in this larger system allows us to see not just where we are, but how everything in the universe is organized on the grandest scales. The local group contains more than 50 known galaxies, although the exact number continues to grow as faint dwarf galaxies are discovered. The two dominant members are the Milky Way and the Andromeda galaxy, each surrounded by a collection of smaller satellite galaxies. The third largest member is the Triangulum galaxy, which is significantly smaller but still a substantial spiral system. Together, these galaxies are bound by gravity, forming a relatively isolated system within the expanding universe. Within the local group, galaxies interact through gravitational attraction, orbiting around common centers of mass and occasionally merging over long timescales. Unlike the expansion of the universe on very large scales, the local group is gravitationally bound, meaning that its members are not drifting apart, but are instead held together as a single system. This makes it a special region of the universe where local gravity dominates over cosmic expansion. The Milky Way's position within the local group is not fixed in a central or dominant role. Instead, it shares gravitational influence with Andromeda, and both galaxies are slowly moving toward each other. This mutual motion is part of the long-term evolution of the local group, which will eventually result in the merger of its largest members into a single large galaxy. In this sense, the local group is not static but evolving. Beyond the local group lies a much larger structure known as the Virgo cluster, a massive collection of hundreds of galaxies bound together by gravity. The local group itself is part of the outskirts of this cluster, meaning that our galaxy is located in a relatively small and quiet region of a much larger system. The Virgo cluster is one of the closest large galaxy clusters to us and serves as a reference point for understanding large-scale structure in the universe. Even larger than galaxy clusters are superclusters, which are vast networks of clusters and groups connected by filaments of galaxies and dark matter. The Milky Way is part of the Virgo supercluster, which spans hundreds of millions of light-years. Within this supercluster, galaxies are arranged in a complex pattern of filaments, sheets, and voids, forming what is often described as the cosmic web. The cosmic web is one of the most striking features of the universe on large scales. It consists of long, thin filaments of galaxies separated by enormous empty regions known as voids. Galaxies tend to form along these filaments, where matter is more concentrated, while the voids contain relatively few galaxies. This structure emerged from tiny fluctuations in the early universe, which were amplified over billions of years by gravity. Dark matter plays a crucial role in the formation of the cosmic web. In the early universe, small variations in the density of dark matter created regions where gravity was slightly stronger. Ordinary matter was drawn into these regions, eventually forming galaxies and clusters. Over time, these structures grew and connected, forming the large-scale network we observe today. The Milky Way, like all galaxies, is embedded within this cosmic web. Its position is determined by the distribution of both visible and dark matter on large scales. While it may seem insignificant compared to the vastness of the universe, the Milky Way is actually a typical spiral galaxy, representing one of many similar systems scattered throughout the cosmic web. One of the most important insights from modern cosmology is that the universe is not random in its structure. Instead, it follows a pattern of organization that spans from the smallest scales of stars and planets to the largest scales of galaxy clusters and superclusters. The Milky Way is one part of this hierarchy, connected to everything else through gravity and cosmic evolution. On the largest scales, the universe is expanding. This expansion is driven by the stretching of space itself, causing distant galaxies to move away from each other. However, this expansion is not uniform in its effects. Within gravitationally bound systems like the Milky Way or the local group, gravity is strong enough to overcome expansion, keeping these systems intact. Only on much larger scales does expansion dominate, separating galaxy clusters and superclusters. This balance between gravity and expansion creates a dynamic universe where structures form, evolve, and sometimes dissolve over time. Galaxies like the Milky Way are stable on short timescales, but are part of a much larger evolving system that changes over billions of years. The study of the cosmic web has been greatly enhanced by large astronomical surveys that map the positions of millions of galaxies. These surveys reveal the filamentary structure of the universe in extraordinary detail, showing how matter is distributed across vast distances. The Milky Way is just one point in this enormous map, but its study provides important information about the processes that shape the universe as a whole. Understanding the Milky Way's place in the universe also helps us understand its origin. The galaxy formed within a region of higher density in the early universe, where dark matter and gas began to collapse under gravity. Over time, this region grew into a galaxy and later into part of a larger group of galaxies. This hierarchical process of structure formation is a fundamental feature of cosmology. The same physical laws that govern the motion of stars within the Milky Way also apply on the largest scales. Gravity operates everywhere, shaping the formation of structures from planets to galaxies to clusters. This universality allows scientists to use the Milky Way as a laboratory for understanding the broader universe. Even the chemical elements that make up the Milky Way are part of this larger story. The hydrogen and helium that formed the first stars were created in the early universe, while heavier elements were produced inside stars and distributed through supernova explosions. These elements eventually became part of new stars, planets, and galaxies, creating a cycle of matter that spans cosmic time. In this way, the Milky Way is both a product of the universe and a participant in its ongoing evolution. It has been shaped by past interactions, continues to evolve through present processes, and will be transformed by future events such as galactic mergers. Yet it remains part of a larger structure that extends far beyond what we can directly observe. The idea of the cosmic web also challenges our perception of emptiness in space. What appears to be empty regions between galaxies are actually vast voids with extremely low densities of matter. These voids are not truly empty, but they contain far fewer galaxies than the filaments that surround them. The contrast between dense and empty regions is what gives the cosmic web its structure. The Milky Way resides in a relatively average environment within this web. It is not in a dense cluster core, nor in a completely empty void, but in a region where galaxy groups are moderately spaced. This environment has likely influenced its evolution, allowing it to grow through mergers while avoiding the extreme conditions found in dense clusters. As we look further into the future, the role of the Milky Way within the universe will continue to change. The local interactions with Andromeda and other nearby galaxies will reshape our immediate cosmic neighborhood. Over much longer timescales, the expansion of the universe will carry distant galaxies beyond our observable horizon, gradually isolating local structures into separate island universes. Eventually, the local group will evolve into a single merged galaxy, surrounded by a vast emptiness as more distant structures recede beyond visibility. In this future universe, observers within the Milky Way galaxy may no longer be able to see other galaxies beyond their local system, leading to a very different understanding of the cosmos. This future scenario highlights an important aspect of cosmic evolution. The universe is not static, and our ability to observe it depends on both spatial and temporal context. What we see today is only a snapshot of a much larger and evolving structure. In the end, the Milky Way's place in the universe is both specific and universal. It is a single galaxy among billions, yet it reflects the same physical processes that shape all galaxies. Its structure, motion, and evolution are governed by laws that apply across the entire cosmos. By studying the Milky Way, we are not only learning about our own galaxy, but also about the universe as a whole. It serves as a bridge between the local and the cosmic, connecting our immediate surroundings to the largest structures known to exist. The final perspective is one of scale and connection. From planets to stars, from galaxies to clusters, and from filaments to the cosmic web, everything is part of a continuous structure shaped by gravity and time. The Milky Way is one thread in this vast tapestry, and through it we gain insight into the nature of the universe itself.